Hi for Einstein. Here we are going to start chapter 4, heat. I wish that you all had really go through the chapter 3 that I posted previously. So now we are going to chapter 4 about heat. The first term that we are going to learn is thermal equilibrium. Okay, so this is not a new concept at all because you learn it in lower secondary study. Okay, so before you understand thermal equilibrium, there are few terms that you have to really know. What is temperature? Yes, you learn that temperature is the degree of hotness, right? Is the degree of hotness. In form 2 you learn that. Okay, means that this thing hot or cold, we call it temperature. Okay, then what is heat? Heat is a form of energy. Okay, it is form of energy. When you come to form 4, it always linked to kinetic energy of particles. Okay, so it always linked to kinetic energy of particles. Means that when I say that something is hot, the average velocity of the particles in this box, let's say this is very hot. I said that it is very hot means that the average velocity of the particles in the box is very fast. Okay, if I have something that are very cold, so means that the average velocity of the particles in the box is actually slower. So that is how we link heat to the kinetic energy of the particles. Okay, so now what is the unit of temperature? I hope that you still remember temperature we learned in degrees Celsius, right? So and then when we come to form 4, we have another unit, we call it Kelvin. This is SI unit. So all the calculation that when we mention absolute temperature, we are actually using Kelvin. This one you have to pay extra attention. So what is the energy of heat? That is joule. Temperature we can measure using thermometer, right? So now we have, before we go to thermal equilibrium, we have to understand kinetic theory of particles. Kinetic theory of particles, that is also not a new thing in your, because you learn it in form 2. Kinetic theory said that all the particles, let's say I have a closed container, so all the particles inside actually move randomly. This is what we call Brownian movement. So it moves randomly. Randomly means that you cannot predict the direction, you cannot predict how it moves, the velocity, it's just random. It moves randomly in all direction, and when it collide with the wall of container, it collide elastically. Okay, so this is what we call kinetic theory of gas or particles. You have to remember it moves randomly and it is moving in all direction, and it is discrete, means that it is alone. It does not bond with others molecule or particles. Okay, so it is alone, it is discrete, and it is tiny. Okay, so kinetic theory just that this thing move in Brownian movement. Okay, Brownian movement. This is not a new thing for you, this is not a new thing for you, but then when we combine these two, we have to understand what is thermal equilibrium. Let's say I have two steel bar. Let's say this one is very hot, okay, and this one is very cold. So what will happen eventually is that the temperature will flow from hot to cold, right? So let's say this is 100 degrees Celsius and this is 10 degrees Celsius. So after, let's say 1 or 2 hours, you can actually predict that this thing, it will become somewhere in between 10 and 100 degrees Celsius, right? So that is what we call heat flow. Okay, does it mean that there is no heat flow from cold to hotter area? No, because they actually heat flow from colder area to hotter area to colder area, but then this one is slower and this one is more. So we said that the net heat flow is actually from hotter area to cold area. Okay, so now we have to learn what is thermal equilibrium. Thermal equilibrium can be achieved when there is thermal contact. Thermal contact, like this is thermal contact because they are touching each other, that it allows heat to flow. When there is thermal contact, and then once it reaches thermal equilibrium, there will be no net heat flow. No net heat flow. Okay, so I want to see the keyword, no net heat flow between two objects in thermal contact. That is what we call thermal equilibrium. Okay, thermal equilibrium. So how does it work? Means that if these two things already in same temperature, says 60 degrees Celsius, 70 degrees Celsius, 70 degrees Celsius, means that the heat flow from A to B equal to the heat flow from B to A. So there is no net heat flow between these two objects which is in thermal contact. So this is what we call thermal equilibrium. Okay, so I hope that you can remember, because this is the definition that I'm going to ask in class. Remember, I repeat, no net heat flow between two objects in thermal contact, which means they share the same temperature. Okay, the temperature is equal. So this is our thermometer measure temperature using the principle of thermal equilibrium. Okay, so this is the first part that you have to remember. Okay, now we go to specific heat capacity. Okay, so we have heat capacity, we have specific heat capacity, we have latent heat, and we have specific latent heat. It sounds like new thing for you, right? Okay, so let's make it simple. So if I have a glass of water and it is in room temperature 25 degrees Celsius, how much energy that I should supply so that it can increase to 26 degrees Celsius? Means that the increment only 1 degree Celsius, right? So I want to only increase that one temperature. So what is the energy that I need to provide? You still remember I said the temperature of something or particles is actually linked to the kinetic energy, right? So if you want to make the particles moving in faster velocity, you have to provide energy so that the particles inside can move in faster motion, faster manner, then you can increase the temperature. Okay, so what is heat capacity? Is the energy needed to increase. Okay, it's the energy that needed to increase, or is the amount of heat needed, or is the energy needed to increase 1 degree Celsius of the substance. That is what we call heat capacity. Of course, heat capacity, it doesn't look so accurate, it doesn't look so professional, because we never know what is the mass of this thing. So to make it something that more stable, we have to consider the mass of the water, right? Let's say now I have 1 kg of water. So the energy that supply to heat out the water from anything 1 degree Celsius to 2 degrees Celsius, we always take 1 degree Celsius changes. So that is what we call specific heat capacity. So specific heat capacity is the amount of heat needed, or amount of energy needed to increase 1 kg of substance by 1 degree Celsius. Okay, so I hope that you understand. I repeat, is the heat or energy that needed to increase 1 kg of substance by 1 degree Celsius. That is what we call specific heat capacity. Okay, so from just now until now, we learned actually 3 terms. First one is what is thermal equilibrium, second is heat capacity, and third is specific heat capacity. Okay, so you have to pay attention to the state of the particles here. It is still liquid to liquid, right? There is nothing like solid to liquid or liquid to gas, right? So what if we have changes of physical state? For example, I have ice cube here, okay, that I melt the ice cube from 0 degrees Celsius of ice cube, I melt it to 0 degrees Celsius of water. Okay, so what is the energy that needed to make it change from one step to another step? Okay, that is what we call latent heat. Okay, latent heat. So what is latent heat? Latent heat is the heat that or heat energy or amount of heat that needed to change, okay, the substance from one state to another state, from one state to another state, another state without changes of temperature. Without changes of temperature. Yeah. So again, it is not so, this is L, it is not so professional, or it is not so specific because we never know the mass. So now we have another terms. Okay, come here. Number 5. You know what is this? Specific latent heat. So whenever you see specific, it is actually refer to 1 kg. Specific latent heat means that the energy that needed to change 1 kg of substance. Okay, 1 kg refer to specific. 1 kg of substance from one state to another state. Without the changes of temperature, without changes of temperature. Okay, so this is roughly of the idea, that 5 terms that you have to know. We have thermal equilibrium, heat capacity, specific heat capacity, latent heat, and specific latent heat. Okay, so we have actually another things that you have to know here, that is absolute zero. Absolute zero. So what is absolute zero? When you look at the word absolute in this chapter, we have to use, we cannot use degree Celsius, but we have to use the unit of Kelvin. Okay, how many Kelvin of how many Kelvin and so on. Absolute zero means that it is very cold. People say that the coolest temperature that we can achieve is actually 0 Kelvin. It's not okay, this is 0 Kelvin. Okay, so the temperature of universe, outer space, is roughly 3 Kelvin. Okay, so what is actually Kelvin, and what is actually 0 Kelvin? So when we talk about absolute zero, it only can be theoretically achieved, okay, in gas. Theoretically achieved, it doesn't really achieve in reality. Theoretically achieved when the temperature equal to 0 Kelvin, which means the kinetic energy of the particles equal to 0. Means that there is no kinetic energy at all. That's why you have 0 Kelvin. So this is what we call absolute zero. Okay, so we will learn furthermore when we come to the calculation. That will be your second part or even third part of your study. Okay, that's all for the first part. Make sure you memorize all the definition from thermal equilibrium, heat capacity, specific heat capacity, latent heat, and specific latent heat, and absolute zero. Actually, all this in your notes. Please get it from your Google Classroom. That's all. Thank you, class.